So starting with the topic energy and enthalpy, we've seen up to this point that a system can exchange energy with its surroundings either by transferring heat through the boundary between the surroundings and the system or by doing the work. Work can be in the form of expansion work or non-expansion work. So what we're seeing here is that there is a connection between energy and enthalpy. So we'll know that what is enthalpy and what is the connection between energy and enthalpy. So basically, the question is what is enthalpy, and the answer to this is that enthalpy is the change in internal energy. Internal energy is the total energy present inside a system. Using the symbol Q to represent the transferred heat and the formula W is equal to minus P into delta V, we can represent the total change in internal energy of a system. So the change of internal energy, which is the total heat content of the system, which is also known as enthalpy, is delta E equal to Q plus W, which is equal to Q minus P delta V, where Q has a positive sign if the system gains heat and a negative sign if the system loses heat. So the basic statement mostly we take here is delta H is equal to delta E plus P into delta V. Delta H here is the enthalpy change and delta E is the internal energy plus P delta V. So the delta H, which is known as the change in enthalpy, can be called as heat of reaction or the enthalpy change. So enthalpy change is an extensive property, and the sign convention goes like Q will be positive if the system gains heat, and Q is negative if the system loses heat. So enthalpy is a state function and its unit is joules, and change in enthalpy can be also measured. Note that only the enthalpy change during a reaction is important. As with internal energy, enthalpy is a state function whose value depends only on the current state of the system, not on the path taken to arrive at that state. So we don't need to know the exact value of the system's enthalpy before and after a reaction. We just need to know the difference between the final and the initial states, which means the difference of the enthalpy change. Here is a derivation of when delta H is equal to QP. If we take a look at the two ways in which a chemical reaction might be carried out, on the one hand, a reaction might be carried out in a closed container with a constant volume so that delta V is equal to 0. In such a case, no PV work can be done, so the energy change in the system is entirely due to heat transfer. But we indicate the heat transfer at constant volume by the symbol QV, where QV will be equal to delta E at the constant volume condition. The condition for the liquids and solids, where delta V is equal to 0, which means the change in volume is equal to 0, delta H is nearly equal to delta E. Here, change in enthalpy is equal to heat of reaction at constant pressure. In a car's engine, most of the work done on the pistons comes from the expansion of the product gases as a result of their temperature increase from the heat transfer of the reaction. Here is some basic information about thermochemistry and thermodynamics. So thermochemical equations and thermodynamic state are interrelated. A thermochemical equation gives balanced chemical equations which has the value of enthalpy change along with it. So we use enthalpy change to understand the amount of heat released or absorbed when reactants are converted to products. So when we are considering reactions, we must consider the thermochemical situation occurring during the reaction. In the combustion of propane or any other gas, the thermochemical equation, for example, is given above. So this equation shows us the value of delta H, which is the heat content. So we must know, if we're talking about the thermochemical equations in thermodynamic standard state, we should know that we are going to discuss the enthalpy change wherever we're considering reactions. Whether there are combustion reactions or any other sort of reactions, we always consider what type of heat content changes occur. So, if you want to confirm that all the measurements are calculated in the same way, we have different reactions in this thermochemistry and thermodynamics. So, there are a set of rules which define the thermodynamic state. So, thermodynamic standard state means that the stable form of a substance at 1 atm pressure and at a specific temperature, usually which is 25 degrees Celsius, 1 molar concentration for all substances in solution is the most stable form. And this state under these certain conditions will always or forever will be known as thermodynamic standard state. When we take the measurements under these standard conditions, which is the 25 degrees Celsius temperature and 1 atm pressure, you should always remember this. So when we take the measurements, we must use some symbol to report this. So there is a symbol of a subscript used as an indication sign that the standard conditions are provided. So it is really very common thing to understand that when a standard enthalpy will be measured under these standard conditions, it will always be known as standard enthalpy of reaction. So standard enthalpy of reaction basically means that the enthalpy change which is measured or calculated under these specific conditions, which are the rules. Some of the definitions were very basic, so I thought I can explain you through the slides. So the next concept I'm going to explain is about an example. Let us take an example about a reaction. The reaction of propane with oxygen in thermodynamic standard state means that the propane will react with oxygen at standard conditions like 25 degrees Celsius temperature and 1 atm pressure. So we will measure the enthalpy change at this point, and at this point the measured enthalpy change will be thermodynamic standard state. So, a thermochemical equation will specify the amount of each substance used, and therefore, the equation of the combustion of propane in this case will be the reaction of 1 mole of propane gas with 5 mole of oxygen, as we have to explain each and every detail here. And the enthalpy change calculated will be at standard state. So, this will be standard enthalpy change. So, in this specific reaction, the amount of heat released will be the enthalpy change. An important point to notice here is that physical states of the reactants and the products in the reaction or specific thermochemical equation must be specified. Like we have to write the solid state, whether it is the liquid state or the gaseous state, we have to explain it. Whether it is the aqueous state, we will apply the words like S, L, and aqueous, AQ for aqueous on the products or the reactant, so we can explain the state. So the enthalpy change for the reaction of the propane with oxygen, as we took an example before, is delta H naught minus 2044 kilojoule. And if water is produced as a gas, but delta H naught is minus 2220 kilojoule if water is produced as a liquid. So there is a difference because the energy is released in the form of steam. If liquid water is produced, delta H is larger. Larger delta H means more negative form, but if gaseous water is produced, delta H is smaller, less negative, because 44 kilojoule per mole is needed for the vaporization. So these things were quite simple. I will explain you through the slides that enthalpies are also of two types, which is the chemical and the physical changes. So almost every change in a system involves either gain or a loss of enthalpy. Enthalpy means heat content. The change can be either physical, which is the physical enthalpy, and can be chemical, which is the chemical enthalpy. Again, enthalpy means the heat of the reaction because it is a measure of the heat flow into or out of the system at constant pressure. If the products of a reaction have more enthalpy than the reactants, then it means that the heat has flowed into the system from the surroundings, and delta H has a positive sign. This is a sign convention for the enthalpies of chemical change. And reactions in which the system gains heat are said to be endothermic, which means within. So the heat flows inside the system. For example, in the reaction of 1 mole of barium hydroxide octahydrate with ammonium chloride, for example, it absorbs 80.3 kilojoule from the surroundings, which is the delta H naught. And if the products of a reaction have less enthalpy than the reactants, then it is obvious thing that the heat will be flowed out of the system to the surroundings, and the surroundings temperature will rise and delta H will have a negative sign. This convention is really very important. Reactions that lose heat to surroundings are said to be exothermic. So this is important to differentiate between exothermic reactions and endothermic reactions. Out, exo, heat flows out. So, the thermite reaction of aluminium with iron oxide is an example of this exothermic reaction. And as noted previously, the value of delta H given for an equation assumes that the equation is balanced to represent the numbers of moles of reactants and products, that all substances are in the standard states, and that the physical state of each substance is specified. The other type is the enthalpies of physical change. For example, the block of ice at low temperature, and it slowly increases its enthalpy by adding heat, and the initial input of the heat, which causes the temperature of the ice to rise until it is reached by 0 degrees Celsius. So additional heat would then cause the ice to melt without raising its temperature, as the added energy is expended in overcoming the forces that bind the molecules together in the ice block. All these concepts were to understand the basic concept of calorimetry and heat capacity. I have used these pictures here to make the concept more clear by visual representation. So calorimetry is the method to calculate the heat content of some gas or the reaction or the products and reactants together all together. So the amount of heat that is transferred during a reaction can be measured with this device known as a calorimeter. As we see here is that calorimetry is just an insulated vessel which has a thermometer to measure the temperature and a stirrer to move the reactant and a loose fitting lid that keeps the contents at atmospheric pressure. So the reaction that takes place inside is insulated by the vessel and outfitted with a loose fitting top and a thermometer and a stirrer, which completes the calorimeter. The reaction is usually carried out inside the vessel, and heat evolved or absorbed is calculated by the thermometer present inside a calorimeter. And also, the pressure inside the calorimeter is constant because of the equivalence to the atmospheric pressure. So, the temperature measurement makes it possible to calculate the enthalpy change. For example, delta H is calculated by this. And this type of calorimeter is usually used to measure the enthalpy change for reactions of salt dissolving in water, such as the reaction that occurs in hot packs and cold packs. The next one is the second type of a calorimeter, which is much more complicated than the simple type of calorimeter, and it's bomb calorimeter, and it's used to measure the heat released during a combustion reaction. Combustion reaction is a highly flammable reaction. It is a burning of a substance that can catch a flame. So it also has thermometer, stirrer, ignition wires for the combustion inside the chamber. And oxygen atmosphere is given to the gas, and there is a simple cup inside to put the the reactants, and there is water to measure the reaction temperature. So when the temperature rises, the reaction is carried out inside that steel bomb. That is why it is known as a bomb calorimeter. So that when the temperature rises, the heat evolved is transferred to the bomb and surrounding water, where the temperature rise is measured. The sample is said to be placed in a small cup and sealed in an oxygen atmosphere inside a steel bomb that is itself placed in an insulated water-filled container. The resultants or the reactants are ignited electrically, and the evolved heat is measured from the temperature change of the surrounding water. Since the reaction takes place at constant volume, other than the constant pressure, the measurement provides a value for delta E rather than delta H, but this is going to be another topic in the next video. Mostly the chips or lays we eat, the potato chips, the food content or the caloric content of this food is measured in such a bomb calorimeter. So we know that when a calorimeter and its contents absorb a given amount of heat, the temperature rises that results depends on the calorimeters heat capacity. Heat capacity, we all know from 9th 10th grade that it's the amount of heat required to raise the temperature of object or substances by a given amount, and a relationship that can be expressed by the equation C is equal to Q over delta T, where Q is the quantity of heat we all know and delta T is the change in temperature. So we can assume that the greater heat capacity, the greater amount of heat needed to produce a given temperature change, to rise that temperature change or to bring about that temperature change. So we can relate this as the heat capacity of the seawater is more than a tub full of water or a coffee cup full of water. It takes a lot more heat to warm the ocean than the coffee cup. As we all know, heat capacity is an extensive property, and to compare these different substances, it's useful to define a quantity called specific heat capacity, or simply specific heat, denoted by C, which is the amount of heat necessary to raise the temperature of 1 gram of a substance by 1 degree Celsius. Some of the values are given here for your information.